Welcome. I will try and crank through this reasonably quickly. I am hosting you this evening, beer and pizza at Doug. Come and have a look at our immersion cooling data center. Probably a lot of you have already seen it. If not, come and have a look. So what I want to do here is talk about a data center we built recently in Houston. And so this data center is quite unique. It's probably the greenest data center in the world at the moment. And we finished it just a couple of months ago. And so it was a lot of my time traveling back and forth to Texas, getting this data center built. And one of the things we did with this data center is we sort of went a little bit crazy on efficiency. So I'll give you a flavour for some of the slightly silly things we did and some of the really smart things we did, and give you an idea of what it's really going to give us in terms of as a company. So first of all, we're Doug. We're an oil and gas service company at the moment. We do work all around the world. Yes, seismic processing is our game at the moment. We are moving into the high performance computing industry and providing cycles for people. So that's another field we're moving into. What really drove this data center was a application called full waveform inversion. Full waveform inversion consumes ridiculous amounts of compute, scales, I think it's frequency to the power of 4, and just gets completely silly at the big end. And really, geophysicists want to run 125 hertz full waveform inversion. Currently at the moment, using other people, they can probably push out to about 15. So they've got a few thousand times more to go in terms of compute. We're pushing that envelope a long way. I have no idea what our highest frequency projects are at the moment. But we're now offering this high frequency full waveform inversion, which gives you an absolutely magnificent picture of the Earth from your seismic data. You sort of go from what's in the bottom right corner, which is lacking a lot of detail, reasonably smooth, to a velocity model of the Earth shown there, which sort of gives you much higher fidelity of what's going on below the Earth's surface. Just to give you an idea, what takes a boat 10 seconds to acquire currently takes about 30 hours of compute on a very high performance CPU. So there's a little bit of a mismatch. You can acquire the data way faster, you can process it on a single machine. And so automatically, to get back up to a reasonable time, you're talking about cluster computing. Again, you need about 10,000 CPUs to keep up with acquisition. What are we doing about it? Well, we're heading, like a lot of the big sites, in the Exascale direction. This new data center was all about that. We're looking at this first part of the data center holding about 40,000 nodes. At the moment, they're KNL nodes, so Xeon Phi. It's about 15 megawatts. It's full immersion. We'll get about 250 petaflops with the current KNLs in that facility. Add a technology change to that, sometime maybe now, next year, whenever, you'll be pushing up towards an exaflop in that facility. Let me give you an idea for us what that means. It means 80,000 network cables, 20,000 power cables, 240,000 DIMMs, a network that scales to 40,000 nodes, and I'll be talking a little bit more about that later. We're also talking about 500,000 litres of fluid, 500 big IBCs. We need a file system that'll do a little over a terabyte a second, we think. And we need to get 15 megawatts of energy out of the room and dissipate it into the air. To give you an idea, to do that with water, which is what we're using, you need 800 litres per second of water to get that energy out of the room. Your fire reel that hangs off your office building, that little red thing there, does half a litre a second. So we have these massive pipes that are about this diameter, the same as what goes up to Kalgoorlie, and they're doing 800 litres a second. So that's what our main header in the facility will do. Power costs get rather insane, and it's that power which is all important. What is a data center? A really expensive way of turning electricity into heat. In that process of taking all your electricity and converting it to heat, we want to get as much compute as possible out of it. I think we've all seen the stats. I think data centres now use more energy than the United Kingdom, and they'll take over the world's energy usage, probably not in the too distant future. Immersion cooling. This is one of the things that we jumped into quite some time ago. The driver was to save energy. We've taken that to the extreme. It allowed us to build this data centre. And we built some really nice features into this data centre which wouldn't have been possible without immersion cooling. So we do full immersion. Again, the simplicity of immersion cooling completely changes the way you think about putting compute into a data centre. So, some of the things we did. Power efficiencies. These are the big ones. Single transformation. We take 33,000 volts, 3-phase, from the utility. We convert that directly with one transformer, and there's one of them in a stunningly good-looking bloke there. We convert that to 415 volts, so 240 volt single phase in the US, at 60 hertz. So it's not quite Australian power, but it's very close. Okay? You would not believe how difficult this makes life in the US. But all the fun guys in town are starting to do it. So again, single transformation gives us two things. It saves us about 5% on losses because most US data centers have to run two transformations. They have 33,000 volts coming in somewhere, and then they take 480 volts from the utility, and you can't use that in a computer because 480 volts is 277 volts single phase. The power supply on the back won't take it. So you then have to down transform again. So by taking 33,000 volts, you actually get on a better power tariff because the energy utility charges you for that first transformation. And there's a loss, 5%, 3%, 2% in that process. By doing a single transformation, we cut down to just one loss through that transformation instead of 2 or 3. PUE does not capture this. You're going to see a common theme in my talking to you about this. So yes, 33,000 volts from the utility, and we transform that inside our data centre. The other thing which happens when you go to Australian power is your power supplies in your computer get more efficient. At 110 volts, the PSUs in your computer are only about 93% efficient, 94% efficient. At 240 volts, or 230 volts, depending on what statistics you use, they're about 96% efficient. So we gain 3% energy use just by moving to 240 volts. So we've gained 3 or 4% by having a single transformation, and we've gained another 3 or 4% just by going to 240 volts and having more efficient power supplies. That is not captured in PUE. Okay? That loss is actually on the positive side of PUE. The other main driver for this is that if you run at 240 volts, you can get 2.5 kilowatts out of your power supply. So most of your nodes you can run on one PSU. At 110 volts, you can only get 1.1 kilowatts out of your PSU. So you can only run, you have to have 2 power supplies on to keep your nodes up. So this change to 240 volts drove an efficiency and also drove a practicality in trying to reduce the number of cables in the data centre. We have no fans on the compute nodes. You've all heard me bang on about this before, I guess. This is a real impact. You take the fans off, because you're immersion cooling, you drop the chassis from 1430 kilowatts down to 1125. Identical workload. Exactly the same compute throughput, and you've dropped this much energy just by removing the fans. Guess what? PUE doesn't capture that. That's a saving we get that doesn't impact our PUE. So what's that, 22% or something? Quite significant. So we've got transformation, better efficiency PSUs, and the 22% due to taking your fans off. We don't do UPS. Well, we do a little bit of UPS on the bits that we desperately need to keep up. But, I mean, to UPS 15 megawatts costs a lot of money. So we don't do it. And it costs us a lot of power. Again, you lose energy going through UPS. Again, UPS efficiency, I think the best ones are around 95% efficient. This is captured by PUE. So we get that one, it's great. Our philosophy has always been try and boot the computers really fast. And that way you're better off spending your money on more compute than you are on a UPS. And then again, you get the continual energy savings. We use evaporation of water or dry in some stages to dissipate to the air rather than refrigeration. So we have these enormous evaporative coolers sitting out the back alongside our enormous transformers. Again, these things only cost about 2% of your energy to run. Refrigeration costs about 30%. And we're doing this in Texas. So if you don't know anything about Houston, 32 to 35 degrees all summer and 100% humidity. It's like being in Bali. Very hot, very humid, and yet you can still do evaporation and only cost you 2% of your total power. So that's driving another sort of 25% saving in our power. That is captured by PUE. These things, to be fair, aren't small. I can't quite see down here, but a person is about that big on this picture. You can see the ladder here. That's a rung between ladder thing there. It's about 8 metres tall, 9 metres tall. They're enormous, and there's a very large number of, well, I think we've got 6 out there at the moment. So again, 30% of our power saving, which is not captured by PUE. We save about another 30%, which is captured by PUE. And where are we going with this? Again, we're hitting a PUE in this data centre of about 1.05. So not as good as what we're doing here in Perth, but pretty good. But on top of that, we have this extra 30%, which isn't captured by PUE, and yet that is saving energy and money. And that part is what makes us, in essence, the greenest data centre in the world. Lots of people can get low PUE, but we've gone below that again. I would argue anybody should be calculating their PUE, should be adding in the cost of their fans, adding in the cost of the transformation of the utility and things like that into there, because that's how much energy you're sucking from the environment in some sense. That's what you're putting back out as heat and CO2. But they don't count that. And so I would say any data centre that does air cooling should automatically be at a PUE of about 1.3, 1.4 and then grow from there. Same number of flops. We haven't compromised compute at all in this. That's important. Again, I mentioned this before, the fact that we run 33,000 volts means that we can participate in energy programs which you can't normally access. You know, if you can sit at this voltage and then you can suck a lot of power in the megawatts, you can really do well on the power rate with the utility. So we do a lot of demand side reduction. We turn off when the frequency on the fabric, on the electrical fabric starts to go, we turn off and we help the utility that way.
Quick question. Could you tell us your average kilowatt hour cost?
I think it's pretty well known in Texas. It's down below 5 cents a kilowatt hour.
That's average industrial?
That's all in average industrial, yeah.
Okay. It's pretty low.
It's very low. You don't do this in the northeast or the northwest. So the other thing that we're doing, which is interesting and incredibly fascinating is we're working with Mellanox on this thing called a multi-host NIC. So basically what you have, well, they've changed this a little bit, but we're going to run 50 gigabits, so we're going to have a 100 gigabit port in their switch. And we're going to take that out to 2 chassis. Each chassis has got 4 nodes. And so we're going to take 50 gigabits into a NIC. That NIC sits on the PCI of 4 machines. So that NIC physically plugs into 4 machines. Each one of those 4 machines can burst to 30 gigabits. That's the bandwidth of the PCI. That's a PCI Gen 3x4. So you can get about 32 gigabits out of each node. But in aggregate, they can't exceed this 50 gigabits. So they can burst to 32, but in aggregate, 50. But within that 4, they can do 32 gigabits to each. Fantastic for a finite difference style code, nearest neighbour style code. Lots of bandwidth. The impact of this actually was significant. It halved the number of switches. Because normally, if you do what we do, you have a 10 gig network, you take a 100 gig switch, you take the port, you bust it out to 4 machines at 10 gig. So you only get 40 gigs of your 100 gig port. We now can get the full 100 gigs from a 100 gig port. So that's quite nice. But it allowed us to halve the number of switches, which had an impact. This is at the top of rack, or this should actually be NTT, next to tank. Let me. Yeah, that's right. Have I got? Yes, here we go. We're back. This had an impact on the spine level of our network. So we could reduce the number of total, we basically halved the number of switches in our data center by doing this multi-host NIC. But more importantly, this thing came into play. Massively reduced the power and cabling. These NICs, one NIC, uses what? 10 watts. Nothing. You've got 40,000 of them, which is what we're heading towards. 10 watts by 40,000 is 400 kilowatts. If you can reduce that by 3/4, you go from 400 kilowatts to 100 kilowatts. Oh, sorry, I lie. Yes, you go to 100 kilowatts. So you've saved 300 kilowatts in power. And in anyone's language, that adds up to a significant amount of money. Again, this efficiency, an efficiency gain on our network, not captured by PUE. And yet, saving energy, saving dollars on how much you actually spend. So this is just from a smartly designed network. They stay in real estate, location, 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 and that is the same for data centers. We chose this data center that we're in, the building that we're in, very carefully. It's right next door to one of the largest switching facilities in Houston, which means that, well, this switching facility's got a few hundred megawatts in it. It's got plenty of capacity. It's got dual massive feeds, north and south. We reduce transmission losses. We're not carting it via cables under or over the road a long distance. It means cars can't hit it. There's not many switches in the way. All of these things reduce the chance of an outage. Again, reduce transmission losses. PUE doesn't capture that. But it saves you in the US, this saves you $1, because they do actually charge you for transmission, and saves you energy, and well, the world energy and things like that. We also chose a data center, this was the other thing, that's on a hill. When you go to this data center, it doesn't look like much of a hill. It's on a hump. It's on a hump, exactly right. If you go up on the overpass of the 99, which is just nearby, it's much higher than the hill we're on. But it's just enough to dissipate the water to all the houses around us rather than the data center, which is important. So again, all of these decisions help us to not have things like UPS. Carefully chosen location means they don't get power outages. Carefully chosen location means we shouldn't be affected by the floods. I've been in Houston for 2 of the 100-year floods. So, pardon? So this is important. This data centre, I mean, density is key for us. We're running about 8.5 kilowatts a metre squared. Or if you're in the US, 800 watts metric per foot squared. Most of your data centres around the world run at about 2 kilowatts per metre squared, so don't let anyone tell you that immersion cooling can't give you density of compute. This of course saves rent, floor space, cable lengths, all those sorts of things. Allows us to fit more compute into the same space. These are all efficiency gains. I mean, cable lengths are important. I mean, I sat down and worked out that, I don't have the number at the top of my head, I should write it in this slide. We have, how many kilometres of copper cable we end up with, how many kilometres of steel pipe and copper pipe we end up in this place. And by carefully designing the centre, packing stuff in as tight as possible, these things get reduced. And that has a significant impact. Sundry things we did. Again, these were all the little things. We're running 70 amp 3-phase circuits to each tank, or each pair of tanks. Again, reduces copper. Reduces breakers in these panel boards, because a 70 amp breaker is the same size as a 60 amp breaker, which is the same size as a 32 amp breaker, which is the same size as a 16 amp breaker. But you get much more power through. So this reduces the number of panel boards we have to have, reduces the cabling, all these sorts of things are massively reduced just by making a decision to go high power. So we're running to the node, to the tank, 3-phase, 70 amps, 415 volts 3-phase, 240 volts a phase. All of these things matter when you've got to pay for them. We run our own custom built PDUs, 72 sockets on a single PDU. Great monitoring, lots of breakers. These are fantastic. Again, reduce the number of PDUs, reduce cabling. We can get much better monitoring. When you have an enormous PDU like this, you can afford to put fantastic monitoring on it and pull that into your BMS system and know how much current everything's using in your facility. So yeah, we build these ourselves, UL or CE certified, whatever you want. We do actually have to cool the space a little bit. We have to cool the air down to about 22 Celsius or 72 F. At night we do warm it up. We don't actually need to cool the air, but for the sake of everyone else has to work in there and everything, it needs to be a little bit comfortable. Again, at least we're not going to the usual frigid air you get in air rooms. We keep it warm and comfortable. Part of this is we don't cool under the floor. We do not use the under area of the floor for transport of air. Because if we did that, we'd be cooling all the copper pipes from the power PDUs, and we'd be cooling the water pipes which take the water outside, which are at 35 degrees. So we want all the energy as much as possible in that water pipe. We don't want to pull it through a crack. So we don't cool under the floor. So under the floor is probably 35, 36 degrees Celsius. Has another benefit, you don't get condensation. So we don't have to, if you have cold water pipes, you have to lag them and do all this stuff. We don't have to worry about that. You're not going to get condensation at 35 degrees. It simplifies our tank design, all these sorts of things. We've gone for a very minimalistic tank, reduces steel, manufacturing costs and all these sorts of things. Reduces shipping and handling. The petrol to actually drive these to site is reduced because we've made them lighter and as minimal as possible. As I keep banging on, reduce manufacturing and materials, less shipping, less stuff to go wrong. We really have this insane focus on the KISS principle. It has massively helped us build this data center, and we're going to be able to scale it really well and saves us a lot of money. We built this data center and we got 13.5 megawatts, for the same price as Microsoft built a data center and they got 1 megawatt. So it's significant. It really is significant. What does it mean? Our data center, achieves 3 times the flots per watt. A PUE under 105, as I've sort of banged on, it doesn't really capture everything. Simplicity breeds reliability and resilience. You can fix most of the things in our data center with a screwdriver and a spanner. It might have to be one of those big plumber's spanners, but you can still do it. Again, we've stripped out every single bit of equipment we can. We've minimised panel boards, we've minimised power distribution. We've gone for big transformers to make sure we've got fewer of them. All of this stuff means less maintenance, less failure, more reliability. In every metric, we've gone after efficiency. And it's paying off really well. I can highly recommend it. Again, none of this would have been possible if you thought about these things in terms of air or traditional data center principles. The company we got to help us build this, the guys who actually hired the contractors, struggled every single day with what we were doing. I can tell you, the power one was really, they struggled with. 415 volts, 60 hertz. It affected everything because it's in the US, you've got to get UL certified. UL doesn't usually deal with 415 volts, so it was all specialised equipment, all reasonably easy to get in reality when you're an Australian or a European or anywhere else in the world other than the US. Turns out in the US this stuff's really hard. But possible and works really well. You can have a look, you probably watched some of our blogs, read some of the articles, it's all out there. You'll see the immersion cooling up at our data centre in West Perth this evening. Again, beer and pizza, 6:30 I believe. Any questions?
What kind of fluid are you using now?
The same polyalpha olefin.
Same oil?
Same oil, same fluid.
Okay.
Yep. No different. Chris?
I was just a little bit surprised by a couple of things said in your bill of materials. I know this is a little bit off to the side, but I was surprised by steel tanks rather than HDPE like your...
Yeah, you need to put a lot of strengthening in the HDPE.
And like copper piping rather than...
Our stuff under the ground is steel. Our stuff coming out of the tanks is copper. We have, for varying things, we do have some copper. Mostly it's all steel though.
I'm surprised it's not plastic stuff, which probably seems to be favouring these days.
Yeah, plastic stuff when it's this big doesn't go so well. Quite literally, you have the big header pipe is about this round. It's enormous, and it's got a reasonable amount of pressure. No questions?
What's the lifetime of the equipment?
Well, we've been using it for over 6 years, and we've never had to replace any of it. It's used in gearboxes, engine oils, eye drops. It's used everywhere. We're not putting it under stress, either heat or mechanical. So it should last pretty much forever.
Because the tank is open, so whether the chance of contamination.
Pardon?
Because the tank is open, so whether the chance of contamination.
Yeah, look, yes, but it doesn't impact the performance. You do get dust in it over time. You can filter it out if you want, or you can just let it go a little bit yellow and leave it. We've had accidentally contamination from various other things, and it's never been a problem.
How beefy are your nodes that are using GPUs and things like that other than the KNLs?
So the KNLs are 2RU, 4 nodes. We run the KNLs, if you know much about them, they have a TDP of about 215 watts. We run them at about 300 watts. They sit permanently pegged at their overclock speed. So mostly KNLs, but we've got a lot of KNCs as well. So the KNC nodes in air run at about 2.3 kilowatts, and a chassis, so 1.2 kilowatts an RU. The KNLs are running a bit under that, 700, 800 watts an RU.
So you mentioned that the power to drive fans in the typical chassis is around 400 watts.
It's about 20%, 22% of a chassis.
Do you have any idea what power required to circulate fluid in the tanks inside?
Yep. Do 200 watts
200 watts.
for about 20 kilowatts. About 1%.
That's a lot better.
That's inside our PUE.
Yeah.
How many nodes per tank?
We have about 26 RU usable. If you come and have a look at our tanks, I'll explain. We have a guy in our office, his name's Ho. He's got the shortest arm. He has to be able to stand at the end of the tank and reach the node in the middle. His arm's about 700 mils long, so the tank's 1.4 metres. No, well that's our standard. No, look, different shape room, different size tanks. We have 4 different size tanks in our various data centres around the world. So it really depends on the form factor. If you can get right along the side of the tank, you don't need, there's no length limit. So.
But there's not a perfect.
No, we tune it for the data centre. Yep. No more questions? Thank you.